So we start off with two normal stars that are in a binary pair. The more massive star becomes a giant, so it may have been a red giant and then it becomes a giant on the asymptotic giant branch, and at each time it'll spill gas onto the secondary star, and that will cause the secondary star to expand and become engulfed. And then the secondary less massive star, that evolves more slowly because it has less mass, and the core of the giant star, because they're engulfed inside an expanding shell, they'll spiral towards each other within this common envelope. The common envelope will be ejected, and then we're left with these orbiting the core of the star, which is basically a white dwarf, orbiting the lighter, less massive star. And they're in a closer orbit. And then here's the most important part. The remaining core, the white dwarf, and the aging companion orbit each other until the aging companion itself becomes a giant, at which point it starts to spill material over onto the white dwarf. The white dwarf accretes the matter until eventually it reaches a critical mass and explodes, causing the companion star to be ejected away. So what would that look like to help you see it? We could imagine perhaps animating that. And so what we're going to want is, let's see, we're going to animate something. And so we'll have a graphics in 3D. And let's see, what we're going to want in that is let's see, a white dwarf that's evolving over time. We're going to want the primary giant star doing its thing. We're going to want that secondary star doing its thing, and there's going to be some accretion from the primary, and there's going to be some accretion from the secondary. And we're also going to have an expanding envelope. So those are the actual components we're going to have in the animation. And I guess I'm going to want the background sky to be black. And I want it to be in shown in a box that's a cube. So I'll make the box ratios 1:1:1, and I'm going to view it from above the orbit, looking straight down on it. So I'll view it down the z-axis. And I'll have some outside lighting just to give a good effect. Although most of the lighting is going to be a glow from the interior of the star, but I'll have it to be alright. And I'm going to watch this thing over a period of so t going from 0 to 1 will be 1 period. I'll watch it for, let's say, 15.5 orbits. So what are these actual things that I'm specifying, these objects that I'm going to be animating? So we had, first of all, the white dwarf and the secondary. We want to be able to define a star, which is basically a sphere. So we're going to have a star, and it's going to be a graphics object, so we'll just put that in brackets. And what's it going to be composed of? Well, basically it'll be a sphere. And that sphere will have a certain location that will change over time, and a radius, the radius of the star, will change over time. So I need a location and a radius. I also want to be able to give that star a glowing color, so I'm going to specify a glow, and why don't we just use a black body spectrum to define the color, and we'll say that will take the spectrum at some temperature. And so I'll need in here also to define a temperature variable. And I also might want the star to have a certain opacity, yet to be specified, but just in general. So I can have an opacity, a temperature. I might as well put the radius of the star here. And then I'll have it at some location. Okay, so that's going to be my basic star. It's going to have a certain temperature, a certain opacity, that is how much you can see into it, a location with a radius. Okay, well, I then might want to go on and say, well, let's consider the primary star. What does that? The primary star is a function of time. Well, it's going to be a star. So let's see. My primary star is going to be a star, and what I have to specify is a temperature and an opacity and a radius and a location. So I'll have some location there. So, well, I'm going to want the temperature to be able to change over time. So let's define a changing function. So we could use a unit step function or so forth, but we want a function that will allow us to change something over time. Basically, I want it to be, instead of just a step, I'm going to use a linear increase. So I'm going to use the function unit triangle. And basically, I'll say that there will be some peak time, and that basically we'll just take t minus t peak, and that'll be my rise rate. That'll be my, when t is less than t peak 0. If I plot unit triangle, it looks like this. You can see at -1 it goes up, it peaks at 0. So when t minus t peak equals 0, it'll be up at its maximum value. I can change the rate at which it rises by putting in a gradient there, so I'll put in a rise rate here. And once it gets to the peak, though, I want it to stay up there. So I don't want it to be that triangle afterwards. So I'm going to define it as being this until we get to t peak, and then after that, it's just the unit step function. I could just make it, well, it's basically the unit step function for t minus t peak. So I could define that, and if I plot that, and so it's a rate, let's just make this 1, and let's make this 3, and I'll plot it for t going to 0 to 6, then we get this. And if I change the rise rate to 2, it's doing it faster. If I change the rise rate to 100, it's like that. 10, it's like that. 0.1, it's like that. So just so I remember what this function looks like, I can take this. So I'm going to define this function up here. And it looks like this. I'm just putting that in the comment. This is what the function looks like. And this is the way it's defined. So I'm going to put that in as an initialization in here. And that can allow me to increase things or decrease things. If I do 1 minus, or I do a negative. Yeah, well, 1 minus would be the easiest way. So I can have a rise rate, a changing function like this. So for my primary star then, I could say, well, let's have the primary star be a hot star. We'll start off with a temperature of 10,000 Kelvin. And we're going to want, what else do we have to specify? We have to specify the temperature, we have to specify the opacity, and we have to specify the radius. So we'll just make the opacity 1 to start with. That is, it's a solid object. And we want the radius. So let's make the radius 0.2 to start with. But now we want the star to expand, remember? So it's 1.2 changer of t0. So what's this changing function doing? If I plot this, t going from 0 to 12. So it changes over a period of 2 orbits up to reaching a maximum 12. So that's when we want the star, how we want the star's radius changing, and it's increasing to 0.2 plus 1.2 at the end of that time. And then I think I'll leave it like that for a while, and then no, let's make it expand sooner than that. We actually want it expanding then 1 and 3. So it expands, and it's finished expanding by the 3rd orbit. And then at a later time, I'm going to have it expand even further to a larger radius, finishing that at time 6. And let's see, for the location, I'll just put 0, 0, 0 for starters. We've got this as a function of time in here, so that's good. Got a temperature, so we could actually go ahead and have a look at this primary star. If we comment out all the rest, comment out all of this, actually from here on, we should be able to have a look at it. There it is. And although I said it expanded, but I can't see it expanding there. Well, that's because I haven't fixed my plot range, so the box always just fits around the size of the box. It's just big enough to show the size of the star. So let's actually now change my plot range and fix it. Let's fix it at something big enough that allows us to see the whole thing that's going to be happening. So we need to specify the plot range up here. So let's specify it, and we'll specify it to be negative x going from negative 10 to 10, and likewise for y and z. Now what do we have? The star sitting there, and then it suddenly expands. Okay. But we know that when the star expands, it also cools down. So we've got 2 expansions. Let's just go back and watch this again. So it's small, expands once, and then it expands again. And so the first expansion is into the giant phase. The second expansion is when it's actually dissipating away. But I just had that happening. I'll make the star disappear after that. So let's see, we could say that's what we've got. But we want, as I said, we want the star's temperature to be changing. At the moment, we've just got it at 10,000 Kelvin, but we can make it change over time. So we'll start at that. But then at the point at which it starts expanding, we'll make the temperature decrease by 80%. So it'll cool down to 2,000 Kelvin, so that's pretty cool. And later on, when it completely dissipates and expands, we'll cool it down to 0. So it's just expanding. This is just an approximation for animation purposes. So this is now going to make the star cool down. So let's watch what happens. It expands. Oh, look, it's cooled down, and it's cooled down even further. It's cooled down, and it's cooled down even further. So it's getting that as red as it possibly can, though, of course. The other thing we're going to do is we're going to make the star's opacity change, because we want it to disappear right at the end. So the other thing we want to do then is we'll start with that opacity, but we'll change it. And we'll change it at that final thing. We'll make the opacity go to 0. So now when we do this, it expands, and then it expands and vanishes. Okay, so that's our primary star. The last thing is I've got it located here at 0, 0, 0, but I actually want it on an orbit. So I need to go back up here and specify what I mean by an orbit. So let's see, my orbit is basically, there's going to be some radius of an orbit, and then there'll be some xy coordinates. So basically I can just use sine and cos and keep the other term 0, and that'll just give me something moving in a circular orbit. And I can say this will be 2 pi t. T equals 1 at the end of one orbit. And this will be 2 pi t. T equals 1 at the end of an orbit. So I need to specify the radius of the orbit. But I could also have an orbital phase, because I could have in here this plus an orbital phase. See, these terms are rising because I've typed this in the past and the system has remembered them. So that's just the phase it has at t equals 0. And so I'll need to specify an orbital phase here, and that'll be a variable, and then it'll be a function of time. So now I have, this will always return coordinates. And so I can go ahead, and instead of putting 0, 0, 0, I could say, well, let's put the primary star, let's see, we'll give it a radius of orbit, I don't know, let's give it a radius of orbit of 1, we'll give it an orbital phase of 0, and we'll let it evolve over t. And now that'll be our primary. That's the way our primary star depends on t, and let's see what we get. Okay, it's moving quite quickly, but there it goes. Let's slow it down. So that's going quite quickly when I animate it like this. But the other thing is, I want to be able to slow the animation down. So let's just go back up in here. I've got the animation. I can say I want the animation rate to be 0.4, and I want the, just to make sure, animation direction to be forward, okay, and then I've got some initialization. So if I run that now, something that's a bit more sedate, and then the star starts expanding and cooling down. then it'll expand again and disappear. Okay. So, now you might be saying, well, what about the white dwarf that's left at the center when the star expands and disappears? Well, I can go and put that in. So far I've defined a primary star, but I could have the white dwarf as well that's left over. So let's define that. And it's also going to be a star. And I don't know, I'm going to give it a temperature of 1,000,000 Kelvin. And I'll give it an opacity of 1 to start with, but a radius of 0.09. And then it'll be in an orbit at some time t. And what will be the orbital parameters in this case? So the orbit in this case, well, we'll just make it also a radius of 1, and it's got to be in sync with this star. So it's inside the star and it'll appear at the end. So if we watch it now, we see we've got the primary star, it expands, and then it starts to expand again, and we can see, or we should be able to see, the white dwarf at the center. So what happened there? Oh, because I haven't uncommented it here. So it's better. So if we have a look now, something's wrong. What's wrong? This message says an unknown box name globe, blah blah blah, sphere has sent a box form for an expression. So I've just missed something out. Maybe a so a star must have a temperature, it's got an opacity of 1, a radius of 0.1, it's got a location, it doesn't need a t there, sorry. Here it is. And then we can see we've got the core left over. Alright, that's good. But of course, there are some other things about the white dwarf. So I'm going to have the radius of the orbit change. So, because, well, no, what am I going to say? I'm going to have the star explode at some point. So, instead of this, what I might have is that I want it to blow up, so I'll just say up to 20, which is outside of the field of view. And I want that to happen at a rate at a time of 14.5. So between 14 and 14.5, it'll expand and blow right out of the field of view. And I'm going to actually just need to decrease the opacity at that time as well. I'm going to do that instantaneously so that we can see, as it engulfs the other star, we can still see the secondary star. So if I run that now, put the star doing this, I'll probably speed it up a bit. And then finally, bang. Okay, it's exploded. Okay, so that's working quite well. Now, we also need, of course, a secondary star. Okay, well, we've got the idea of how we're defining these now, so we're going to have a secondary star. It's going to be a star. And so what do we need to specify for this? Well, secondary star, we need a temperature. Let's see, we'll start the star off at 5,000 Kelvin. We'll give it an opacity of 1 to start with, and a bit of a radius of 0.1 as well. We need to put it in an orbit. So let's see, we'll put it in an orbit that has a radius of 1. We better make the radius of the orbit change we'll leave it as 0, but we'll leave it as is. It's got to have a radius of 1, but it's got to be 50% of the way around the orbit compared to the other star. As a function of t, there's our secondary star. So if we turn it on now, there we have 2 stars. And we see this one's a bit whiter than this one. It's a bit yellower. That one expands up. And we're left with that. All right, now, the thing is, when these 2 stars expand up, they actually move closer together. Their orbit actually changes. So what actually happens, we'll say that the orbit decreases by, let's say, 30%. So let's say that instead of this, that at a later time, it changes by 30%, and we'll have that change happen slowly, but we'll have it finished happening by 6. Remember, we're just animating. This is not a physical simulation, just an animation to get across the point. And we'll have the same thing happen to this orbit here, and then we've got to do the same to the white dwarf orbit as well, which is inside the primary. So now if we do that, and they've spiraled closer together. Okay, so we can see they're closer now than they were to start with, 30% closer. I could, if I just wanted to see that more clearly, I could perhaps come in and just look at this from -3 to 3. And then I'll see this. See 1 star expand. I'll see the other star expand. We should really make that white dwarf really tiny, shouldn't we? Comparison. So then the other star will expand. So what the main thing we were looking at was the fact that they started off further apart. Okay, so when they start out, they're this far apart. After they've coalesced, they're this far apart. So they do spiral in at the point where there's that going on. Okay, so we've got the stars spiraling in. We know that an expanding secondary star should really have a changing temperature. And we know that it's going to expand later on when it reaches its giant phase. So let's have it expanding. Let's see, initially it's that. When it accretes material, let's just have it expanding a bit, corresponding to the accretion of material from the secondary star. But I'm not going to change the temperature due to that. And then I'll have it settle back down again. And then I'll have it expand up like that. So if I watch this now, this going on, the star expands. This one expands because it's accreting material. We have a contact binary. They spiral in together. It settles back down again, but then eventually it's going to become its own giant. Accrete material onto the other star, onto the white dwarf. And eventually the white dwarf is going to explode. And then what happens then? Does this, at the point of explosion, does this star carrying on orbiting around? So that doesn't work, does it? It's got to stop orbiting. So I could say, well, the secondary star, it does this. It's in orbit and has orbital coordinates. But let's see, it does that up until time 14. So we'll say unit step 14 minus t plus unit step t minus 14. And after t minus 14, it's just going to carry on in a straight line. And it's going to be, if I put 14 into this orbital thing here, and look at what this would be, when t equals 14, and that's 0.5. So what I'll get is sine, this will be 14.5, so this will be this will be changing. Initially it'll be 0, t minus 14. It'll be changing at a rate of negative 2 pi, and it'll be out at a rate of 0.3. Hmm, 0.4, I think. Let's see, minus. The ORB goes minus 0.3, the other one goes minus 0.7. So it's actually out at 1 minus 0.3, out of a radius of 0.7 actually. And so minus 0.7 and 0. So I can whiz forward to this point of interest, right up near the explosion, just there. Bang, off it goes. Good, that works well. Around it goes, and then bang, and off it goes. Alright, and I suppose the other final step I can say is that we don't have the temperature of the star changing, do we? Temperature's being fixed at 5,000. Well, I really want the temperature to change. I want it to change by 30%, let's say, as the temperature goes at time 10. And the white dwarf radius is tiny. So they have it going around. I have that one expanding and then dissipating, and then this one cools down, and then this one expands and cools down, accretes material, this tiny dot goes bang. Bang. There we go. Okay, so now we've got a secondary star expanding, going off primary star, we've got a white dwarf. What else do we need? Well, we need some accretion occurring between the stars. So I could define some sort of accretion tube that's going to join these stars together when they're accreting. Remember, this is just it's just an animation. It's not meant to be real physics in terms of, it's not a physical simulation. So basically, I'm going to have a tube. I want to have a tube, and I'm going to make the tube follow a curve. So it's like a hose. And the curve will be a B-spline curve. And I'll get it to follow some points. So up here, I'm going to need to specify some points. And for each point, I want the tube to have a certain radius. So I'll specify some radii. There, so I've got some points and some radii. That's inside the beat, so that specifies the curve. It's determined by these points, a smooth curve, and some radii. And what else? I could also say, well, I want it to have a certain temperature. I'm going to give it a glow, just like I had before from the star. So I'm going to give it a similar sort of treatment here. So I'm going to specify also a temperature. And I suppose I may as well specify an opacity as well. And one other thing, at the end of the hose, or the end of the tube, I don't want to put any sort of cap on there. There is an option to do that. I don't want one. So I've defined some accretion tube here. And then what I need to do is define a set of points to fit that tube along when I have the accretion from the primary. So I'll have some points function, which is going to specify some points. And it's just going to be a series of points. Basically, each of these is going to be just some point on the orbit as a function of time. So we're just going to have a sine 2 pi t. Let's see. So we'll specify some r values as well, I suppose. So let's specify a points function to be some t and some r value, whatever that is, some like that. So it'll be that. There'll be t. There'll be a phase, and an r value. I'll put the r value up. R value, phase, and t. So we'll have an r value. We'll have 2 pi t plus phase cos 2 pi t plus phase and 0. And 0, so that's just going to be specifying some point in space, and then I can have my, let's see, points from primary as a function of time. And so I'm going to define this as a series of these points functions. So I'm going to start off at the secondary with a phase of 0.5. See? Points function. I'm then going to go out a bit. You can see I've worked these out beforehand as a function of t. By a bit of trial and error. It's not perfect. Do a lot better than this. T. And then finally, points function 1, 0, t. And that's going to be my points from primary. That's going to be used to define the shape of the accretion tube. The path of the accretion tube is defined by. You can look up the spline curve to see how they're used. And so then finally I can say, all right, well, my accretion tube from the primary as a function of time will be, it's going to be an accretion tube. And remember, I have to specify a temperature. So why don't I make it, it's from the primary, why don't I make the temperature basically the same as I had in the primary? Because it's stuff coming off the primary, so as a rough approximation, I'll make the temperature that. And I'll make the opacity so I'll make it an opacity of 0.8, but I'll let it appear. The time I want it to appear will be 3.5 orbits, and then I want it to disappear at 5.5 orbits. That's my opacity, and I want it to follow. So the other thing I need to specify are the points. I want it to follow this set of points. Oops. And what about the radii? Well, I basically want it to have radii of 0, 0.3, 0.6, and 1.2. But I want each of those to change. They've got to follow the expansion of the star. So let's make this 3, let's make this 6, and we'll make each of these do this. Okay? So if we do this, now what we should see appear is some sort of accretion tube, but it didn't like that. I've missed something out in initialization. It's probably a semicolon. Something's not right here. Why have I got this? Yeah. Not sure. So here we've got the orbiting stars. Star expands and an accretion tube does not appear, so we've got to make sure that accretion tube appears. Ah well, it's because I haven't uncommented it. So let's go back up here and say, well, I want the accretion from the primary to appear. Yeah. There we are. Well, it's not perfect by any means. Something's not right. Better, but it's not right. Not quite what I had in mind. So let's have a quick look at this. points from primary. 0.5, 0.4, 0.25, 0, 1, 1.6, 1.6, 1. Right. Creation tube primary should be going. Now, what's happened here? I accidentally copied that in there. Right, let's try it again. So we've got them orbiting now. It expands and it's accreting. It's just illustration to be real. Actually, the way it accretes, they merge. The other one expands off and contracts back. All right. Now let's get the accretion going in the opposite direction later on when the other star expands. So we can put in the accretion from the secondary as a function of time. And it's going to be an accretion tube. And, well, we'll have it basically having the same temperature. What do we have for the temperature of the secondary? Did this, and then 10 did that. So we may as well have the accretion from the secondary following the same temperature. So we need to specify the temperature. We need to specify the opacity, points, and the radii. So what about the opacity? Well, I want it appearing. I'll give it an opacity of 0.9. I want it appearing at this point here. So I want it appearing at that point. I'll have it disappear when the other star explodes. So that's the opacity. Now I need to specify a series of points. So let's go ahead and do that. That's going to be something similar to this. We'll call this one points from secondary. And we'll say, all right, well, let's see, we'll give it 0.75 radius to start with, 7.5 R value. We'll give it the next step along a radius of 1, 1.1, and 0.9, and we'll give it some phases of, we've got to be ahead, and then 0.9, and then 0.75, and then 0.5, back to the original star, and we'll call that points from secondary, put those points in here, and we then need to specify the radii of the tube, so we'll have it going, let's see, 0, 0.1, 0.2, 0.3, but I want that changing over time, and basically I wanted to expand up at time 10, change T110. So I should be able to go ahead and run that, and let's see what we have now. we have expanding, greeting, second star expands, contact binary, spiral in towards each other, goes back down. Second star expands, cools down. Should be accreting material, it's not. Ah, God, I keep forgetting to do this. It's because I haven't turned it on up here. Accretion from primary, accretion from secondary. Last thing we'll have is an expanding envelope. So we've watched all of this. We just want to go to the point where that happens, and now it's starting to do this. It's not great. I think something's not quite right there. Okay, so I don't know, I just think that should be increased a bit. They seem a bit small. Let's just run that forward to the point where I get the accretion. That's better. We could even go up to 0.6 maybe. How does that look? It's better. It's better. And then it should disappear at the point of explosion. Boom, off it goes. Good. So we've got everything we need except for one final step, and that is there needs to be this common envelope. And so I'm just going to approximate that as a torus, just for animation purposes. I'm not saying it is a torus or exactly a torus, but here we're making an illustrative animation. So let's define a torus with a certain radius. That is a radius from the center of the, if you like, the donut to the middle of the, to the ring in the center of the hose that's been made into a torus. That is that circle that defines where the tube runs, because I'm going to do this with a tube. I'm going to do this using a module, because there's going to be an internal variable. And so, first of all, I'm going to say, all right, well, I'm going to have this ring that defines the path the torus tube follows. And that's going to be a table of points with x going from, I don't know, 0 up to 1 or 7/8 in steps of 1/8. That'll do. So it's a table of points, and those points are simply 2 pi x. Again, just got a circle, cos of 2 pi x and 0. So that just defines my circle, my ring. And then I'm going to get a tube. What I'm actually going to return from this is a tube that follows a B-spline curve that's this ring with this radius. Okay, so it's just this ring, and then we expand it or contract it by this radius. And the other thing I want is I want that the spline closed. True. So that's that. Oh, that goes inside there. So that's that. Close the tube, and there's my torus defined. And then I want to be able to envelope. I guess we're going to give it a temperature again, we'll give it an opacity, and we have that it has a certain radius because it's going to expand. So basically it's going to be our torus with this radius up here. The other thing is we're going to give it some black body temperature, so let's just go and grab a temperature from up here in star. Same thing. We want to give this a temperature, and we're going to give it some opacity. So that would in general define our envelope, but I just want an envelope that's a function of time. I'm going to turn that on in here. I could actually put the temperature and so forth up here, but just to be consistent with everything that's gone above, I'm just going to make it a function of time and define the envelope down here by calling it expanding. So far this was just an envelope with a certain radius and temperature and opacity. I'll call it expanding envelope, and then it will be an envelope, and I'm going to make it behave in a similar way in terms of temperature to the accretion from the primary. So let's give it a similar temperature behavior to that. I need to specify the temperature, I need to specify the opacity. Well, let's see. I want it to be, let's make it say 0.2. But of course we want it to change with time. We want it to appear once the accretion has started from the first thing, and we'll have it just disappear from view later after it's expanded, because the final thing to specify is the radius, and I'm going to have the radius of this change. I'm going to have it starting off at a radius of 1.5, increasing to a radius of 10 plus 1.5, slowly finishing the expansion at orbit 8. There's my expanding envelope, and I've got that shown here, so I should be able to go ahead and run this now. It's still chugging away from its previous run. Let's run it and see what we get. So, got the first star. It's expanding, starts the accretion, and then, oh, that torus was way too thin. That's not what I had in mind. So, something's not specified quite correctly. That tube in the torus was way too thin. What did I get wrong? In here, I haven't specified the base of the tube. Specify it to be 1. Let's try running that again. So here we have it orbiting. Primary star expands and accretes onto the secondary star. We have contact accretion. We have ring of material. Might make that a bit darker. 0.2 is maybe a bit faint. Put it up at 0.4 and 4. See how that looks. Run it forward. Yeah. Personally, I might bring it back to 0.3. And we might want to zoom out a bit now. We can see we've got this ring of material expanding and going out of view. There it is. Secondary, we get the ring of material forming and expanding out. I might have that one thing I would say is I've got the secondary star, sorry, the primary star expanding between time 5 and 6, and I've got the accretion tube expanding between 4 and 8. this forming, got this going like this. Yeah, that's good. And it goes off like that. I could actually move out and observe this from further away now, if I want to. At the moment I'm quite close. Come all the way back up here. Why don't I go out to -5, 5. I could, of course, specify that as a parameter, I guess. Beautiful. There we have it. Then the secondary star expands and starts accreting. Maybe I'll have the accretion start a bit later. Secondary star to expand and start accreting. So I want the accretion maybe from the secondary just to start a little bit, just to appear a little bit later. So at the moment, I'm going to make it happen a little bit faster. So let's just go through that. Da 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 da. Boom. Da 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 da. It's coming on quite soon, isn't it? Let's stop that. Accretion from the secondary. Use that forward and down. Da, 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 da. That's better. Star expands, starts accreting, just like we had. Is that what we had back here? Star expands, and then starts accreting. Oof. Star expands, then starts accreting, and then bang. Off it goes. Beautiful. So that's how we create an animation of Type 1 Supernova. Finally, what we might do is, say, clean this up. And, oh, I don't know, we could just take this and close that cell so that it's really obvious. And there we have it. There we have an animation. So we can say, all right, this process is illustrated. It's not a full computer simulation. Following animation. One last time. Okay, so that's how I've created this animation.